I have a spring attached to some stationary object, and let's say I know that it takes a certain amount of force to stretch that spring a certain distance, and then I want to find out how much work is required to stretch or compress the string some given distance. So for example, let's say that if you apply a force of 20 newtons, then that spring stretches, let's say 5 centimeters from the equilibrium position. Equilibrium position means sort of its natural state where it's not being stretched or compressed. So it requires 20 newtons of force to hold this spring 5 centimeters from equilibrium position. Then a question would be something like, how much work does it take to stretch this spring starting at equilibrium position out to, I don't know, 7 centimeters, or compress it to 3 centimeters or something like that. Let's compress this 4 centimeters. And I want to calculate how much work is required to do that. And what makes this interesting is that the force changes as the position changes. So you can imagine for the spring at the beginning, when you're pushing it or pulling it, it's easier than after it's stretched a little further. So the further you stretch it or the further you compress it, the more force is required. There's a law that determines how much force is required called Hooke's law, and it says that the force is proportional to the distance from the equilibrium position. So the force is equal to some constant times the distance, which I'll call x, from equilibrium. Work is force times distance, as long as the force is being applied in the direction of displacement, which is the situation that we have. So I need to get my hands on force. I'll use that to get work. I know that it requires 20 newtons of force to go 5 centimeters. And I'm thinking ahead a little bit here. I know that work is usually given in units of Newton meters. So I'm going to change these distances to meters. So instead of 5 centimeters, I'll use 0.05 meters. So 0.05 meters is x. And I want to solve for k. You can divide by 0.05, or you can think of this as a fraction. 0.05 is 1/20th. So if I multiply both sides by 20, I'll get k. So that constant is 400. Now, to get the work that's required to compress this string, I can approximate it by picking some point in here and evaluating the force at that point, and then doing force times distance, where my distance is 4 centimeters. That would give me a really rough approximation though, because no matter which point I choose, if I calculate the force at that point, it doesn't completely represent the force as you move, because as you move, the force changes continuously. So that's what's making this challenging. So your approximation, you can get just by chopping this distance of 4 centimeters up into pieces, grabbing a point from each of those pieces, and calculating the force at each piece. And then you can calculate the work on each little piece by doing force times the little distance of that piece. So my approximation would look something like I'm adding up, so this is a summation notation, adding up force times distance on each piece. Force depends on the x value that I'm grabbing, so you'd usually write something like f of xi. You would let I run from 1 up to the number of pieces, I'll just call it n, and you're doing force times distance, I'm going to call the distance of each piece delta x, and my approximations will get better as I use more and more pieces. I'll have less error. If I let the number of pieces go to infinity, take the limit as that number goes to infinity, it's the same as taking the limit as this length of each piece shrinks down to 0. And when you do that, this turns into an integral. So these are approximations of work that get better as delta x gets smaller. To get the exact work, take the limit of these approximations as delta x approaches 0. Then you get exactly the work. It turns into an integral because you can interpret this as a Riemann sum. You're just integrating the function f dx. We'll be integrating from the equilibrium position to 4 centimeters, and the force is going in the same direction as the displacement, so I'll just make this positive 4 centimeters. If we were going this way, the force would still be going in the direction of positive displacement, so the force would be, I would count the force as positive. The work done by the spring would be negative because it's in the opposite direction as the displacement of the spring. But the work done by us, by the outside force, would be positive. So I'll go from 0 to 4 centimeters, 0.04 meters. And we figured out what the force function was. It was k times x, where k is 400. So now I can just find this antiderivative to finish up the calculation of work. Use the power rule. And when I'm plugging in my bounds, I'm going to think of this as 4 over 100, just to quickly reduce this by hand. So one of these powers of 100 will cancel out with the power of 100 here in the 200. 200 over 100 becomes 2. So in the top I've got 2 times 8. Then in the bottom I've got 1 power of 100 left. So I've got 0.08 Newton meters. And Newton meters are also joules.